The seas around Finland freeze every winter, so dealing with ice is almost second nature to us. We have hundreds of years of excellent ice observation notes from lighthouse and coastal locations, a century of experience building icebreakers and ice navigation, over 5 decades of world-class ice-related research and development work, and the unique experience of building over 200 ice-resistant offshore structures, as well as construction of cold climate harbors, navigation fairways, and channels. Ice engineering involves much more than following guidelines and standard calculations. Just consider the ice thickness problem. In coastal and offshore engineering, we must be ready for extreme ice events. There are faster mechanisms of ice growth than simple static growth. Eranti Engineering and Aker Arctic have been heavily involved in solving key ice engineering problems in projects around the Northern Hemisphere. Let's look at a few examples of our R&D work. Let us first consider the basic problem of level ice load against a hydraulic structure. In some locations, slow and limited ice movements dominate design considerations. In some other locations, major dynamic ice force events are the issue. In some cases, the question is whether the structure is exposed at all to major ice events. There are also multiple ice failure modes to consider: crushing failure, bending failure, shearing failure, freeze bond failure, not to mention a range of instabilities of the ice sheet under pressure. Ice forces on inclined structures can be fairly well defined thanks to verified theories and field experience. However, there is a great deal of uncertainty when it comes to ice forces on vertical or nearly vertical structures. This uncertainty was highlighted several years ago when a massive offshore oil drilling caisson nearly lost its stability in the Beaufort Sea during a dynamic interaction event. 2 series of unique ice indentation tests were performed to get full-scale crushing failure data. Wide and narrow indenters were attached to the front of icebreakers and then driven against ice with instrumentation for ice load measurement. Next, a series of dynamic ice structure interaction tests were performed with a vibrating mass and real columnar grained ice. It turns out that peak ice force is not a pre-given measure, but depends strongly on the response of the structure. Our study found that just a slight inclination of the face of the structure was sufficient to reduce peak ice forces and structural vibration. From this insight, we developed a dynamic ice structure interaction model based on zonal ice failure. It produced results in agreement with a whole range of test results, and it was verified against a number of recorded full-scale ice structure interaction events. The model has since been used in the design of numerous ice-resistant offshore structures. First-year ice ridges can be impressive. They constitute the ultimate threat to offshore structures. Yet the available information on ridge occurrence and their properties is often inadequate for design purposes. For starters, ridge load calculation can be complicated. A key parameter in ice load computation is cohesion of the ridge keel. We traveled to the Gulf of Bothnia to measure this parameter in full scale for the first time ever using a breakthrough test. The principle is simple. Slots are cut through the consolidated ice layer. Weights are then added on the separated ice plate until it breaks through. It turned out to be much tougher than expected to achieve a breakthrough. Mapping the ridge and cutting slots required a lot of energy. Piling enough weight on the separated ice plate took time, but finally the keel gave up. An underwater view of this old ridge keel reveals that ice blocks are partly frozen together. This is the primary cause of keel cohesion. A number of model tests have been performed to study ice ridge failure against a variety of structures. Once we understand that ridge impact angle can vary, ridge load is calculated by adding the solid ice failure component, keel failure component, and components related to rubble kinematics. This puts us in the ballpark, but it is still not a precise answer. We must now define realistically the relevant geometry and properties of the design ridge. This is typically where the most expensive mistakes are made. In this respect, historical notes on ice events, field experience of ice expeditions from different sea areas, information on ice ridge loads on existing structures, and results from icebreaker ramming tests against ice ridges are extremely valuable. Ice management is meant to keep navigation infrastructure operational even during extreme winter conditions or ice events. The problem is often related to brash ice growth, and in some cases, moving ice masses. The accelerated growth of brash ice is illustrated in this picture. When the ice cover is repeatedly broken, free water at the surface is exposed to freezing temperatures. Here we see heat escaping from the freezing layer into the atmosphere. Ice growth is almost linear as compared to the parabolic static ice growth that occurs under the ice cover. The lower the temperature and the more ice you break, the more ice you create. Modern ship propulsion helps considerably in berthing and turning in brash ice. However, when the freezing index reaches 1,000 degree days, berthing and turning become difficult and time-consuming in a busy harbor. The ice collar that forms against the berth wall may prevent berthing even with the help of an icebreaker. Thermal effluents were first used with a surface current generator to focus ice melting effects along the berth wall. As this technique developed, we combined thermal effluents with bubbler lines for ice melting. We have developed and verified our ice formation and ice melting models under well-controlled conditions in the Saimaa Channel. We now possess a complete tool set for analyzing ice formation and melting of brash ice in harbors. And we have the references to go with it. In Arctic harbors that experience up to 4,000 degree days of frost, ice problems escalate as traffic increases. The fact that the melting point of sea ice is higher than the freezing point of salty seawater complicates ice management. A successful year-round Arctic harbor operation may require icebreakers, heat sources, bubbler lines, and an ice barrier to protect the harbor basin from moving ice. Naturally, experience and operational planning are essential for cost control. Whether your ice engineering needs are connected to harbors, offshore wind farms, nuclear power plants, ice-resistant oil and gas platforms, jetties, navigation aids, offshore pipelines and cables, floating structures, channels, bridges, or something else, we at Eranti Engineering and Aker Arctic will provide you with realistic and cost-efficient solutions.